So in the last video, we talked about these catalyst beads into more detail, and we talked about the purpose of the catalyst beads and what they do for us and why we need to put general maintenance on them and why we need to exchange them, because it was really those catalyst beads that produce the CO2 that comes from the combustion reaction. And this is how the entire TOC instrument works, right? Okay, well, once we form the CO2, then the instrument will have to see the carbon dioxide that is getting produced. And again, the more CO2 that I have, the more contamination that I have in regards to my sample. All right, the dirtier my sample is. So if I'm bringing in a drinking water sample, and that drinking water sample has a 1,000 value for my carbon dioxide, then I am drinking pretty filthy, raunchy water, all right? So the detector does this job, and it measures these things for you, and it reports out a value through the computer system and the software about what this number is actually going to be. So this detector is going to be, again, a very important piece of the puzzle. So if my detector goes out, my machine stops, and I cannot utilize my machine, right? Because this is the piece that sees the stuff. And if that piece goes bad, it's an integral piece that has to be functioning before I can trust any data that comes from my instrument, bottom line. So if I go back to my schematic, and I'll pull that up here, we are now making our way through the schematic a little bit more, and we're kind of on the very end of this now, right? So the 8-point valve was here. The 8-point valve sucked up my sample into the syringe. My sample then got purged and mixed with a little bit of acid, and then that went inside of the combustion tube. That combustion tube held my catalyst beads. That combustion tube was heated to 680 degrees, and CO2 was produced in this area. Well, CO2 is going to be pushed out of the tube through the air tank that I have hooked up to my instrument, and CO2 is then going to go through a couple of different pieces on this schematic, and we're going to come back and talk about some of these other pieces. So it goes into what we call a purified water trap. We'll come back to that. And then it goes into what we call a dehumidifier. We'll come back into that too. And then it's going to go through a halogen scrubber. We'll come back to that as well. And then it goes through a filter. And then finally it goes into my detector. And my detector here is this box that has these dashed lines all the way around it, and this is classified as a NDIR. So this is the area now that we're focused on. Again, the other pieces and parts we'll come back to, and we'll talk about those one-on-one, but here we're going to focus on my detector. So this detector is labeled with an abbreviation of NDIR. All right, so what does NDIR stand for? NDIR stands for non-dispersive infrared detector. Now, you probably know that that's going to be an abbreviation that's going to show up on an assignment. What does NDIR represent? What does it stand for? Okay, non-dispersive. Let's start with that first. Non-dispersive means that it doesn't change. It doesn't disperse the light. So this is a very finely tuned detector. And non-dispersive means that it only sees one thing. That's it. And that one thing is CO2. It doesn't look for anything else. Because it's so specific, we can actually get it to read very low levels of carbon dioxide. And when I say low levels, it's not uncommon to read 0.5 ppms, and maybe even lower, depending on your type of machine that you have. Normal drinking water is around a 2 part per million, 2 ppm. So for this instrument, It will be able to detect the regulated drinking water value without a problem, and it can go half of half. Half of 2 is 1, half of 1 is 0.5, easily without a problem. Okay? Now, can we go lower with our instrument? The answer is yes. We can push it. We can go a little bit lower than this. We don't really like to, because there's going to be a gray area where we can't really feel good about the data. Okay? There's going to be a minimal detection limit. Sometimes that's abbreviated as MDL, minimal detection limit. And I just don't really want to go down into that facet of the laboratory. Okay? If I know that the majority of my samples are going to be 1s and 2s, then why do I want to go to the minimal detection limit just to say that I can do it? It doesn't really make any sense. So I always pick areas that the machine is comfortable, that I'm comfortable, that it can clearly identify something without a problem. And 0.5 is kind of that number. So this detector is specifically made to see carbon dioxide. And it does it by using infrared technology. If you've ever seen the movie The Predator, right? The Predator, super killer, good at what he does. And one of his killing techniques, the way that he sees, is through infrared technology. He can just simply look for heat. Heat maps. Different way of looking at this, right? This is exactly how an infrared detector works. So the infrared detector is made a certain way, and carbon dioxide has some movement. That movement can kind of generate some heat, and I'm going to put that in quotes because it's not really true per se, but it gives you a better understanding of how this thing is doing its job. So CO2 is going to be moving. It's going to have a workout routine. And as it's working out, it's going to generate some heat. You get hot when you get on the treadmill, right? So this heat can be measured and it can be picked up by an infrared detector. And this infrared detector, though, is going to be different because this infrared detector is only going to be looking at CO2 and how CO2 works out and how much heat can CO2 give off. That's it. All other compounds will give off different workout routines and different, quote, heat that is liberating from that molecule, and therefore the infrared detector, this one, cannot see those. It is only tuned for that one workout, for that one molecule, and that is it. That's why we call this non-dispersive. We do have infrared technology in the lab. We use it all the time, but that's dispersive. That will see everything, not just one thing, and that's it. All right. The replacement cost here on this detector is around $2,000, so it's something that you hope never goes out. It's also something that you shouldn't really have exposure to. So this is embedded on the inside of the machine. It's also behind a couple of different covers. They really do protect this area as far as the detector goes, because there should be very little amount of work that you have to do on this detector as you have the instrument. This detector should last for quite some time unless you are ignoring other pieces of the instrument that do need to be replaced. All right. This detector, this is just mainly the top of the detector. I would call this the main box of the detector, and that can be ordered. It can be replaced. It requires a little bit of maintenance, but you can do it, and you don't necessarily need a Shimatsu person to come out and do it for you, but it is there for you to order if needed. The reason that I circled that main box on that detector, that main box is actually right here at the very top. Okay, so that is the actual detector, but there's other pieces that come along with this detector as well. So one of the other pieces is number 3 down here at the very bottom, and this piece that sits kind of at the bottom of this setup, this is what we're going to call the light source. All infrared detectors, it doesn't matter, all infrared detectors have to have a light source. This is how they see, okay? So it's like you walking into a dark room. You can't see what's going on unless you turn the lights on. So this infrared detector has to have a light source. It has to turn the light on. And that light source is going to be spot number 3 down at the very bottom. This light source really isn't any different too much than normal infrared detectors and how they're made. And again, this is part of our spectroscopy class. So that's a different day at a different time, but we will talk about how those detectors do their job. But right now, the only thing that you need to know is that a light bulb is required, and that light bulb is the light source, and that's going to be number 3. It's actually not even a bulb. Okay, so don't take that and get confused with it. Maybe I shouldn't have said it, but it is not a bulb. It is made entirely different, but I'll call it a light bulb for now. All right, number two is also an area that's part of the detector, and this is what we call the cell pipe. So as you can probably tell, a light source will shine up this way. It will go through this pipe that they're calling the cell pipe, and then it goes and it hits the detector on this end, which is labeled as number 1. Okay, so 3 parts of a detector: the main detector eyeball part, and then a tunnel that the light and the sample really has to go through, and then the light source that's going to be at the very bottom. All of those 3 pieces get connected together, of course, and those get basically attached on the inside of the machine and secured in a proper location. Again, it is going to be an area that's a little bit more difficult to get to. You don't have to go in and fumble with this stuff too much, and if you do have a problem here, it's probably because of the way that you've operated the machine or the age of the machine itself. So if you do have to replace the detector, it can be done, but it's one of the most expensive pieces that you're going to have to purchase, and this thing is running about $2,000 a pop when this decides to happen. All right. As far as the detector, what's the detector going to do? All right, so I'll show you what you'll see on your screen. Normally in the beginning, when you inject a sample, you're going to see a flat line that shows up on your computer screen. So that flat line means the detector, of course, is not seeing anything. That's why it's flat. Well, as sample goes through the combustion tube, it will now get heated up, it will now combust, and it will now make CO2. That CO2 will eventually go to that detector. And if it gets to that detector, what you'll see is a spike in the signal. This is the detector's way of telling you that it has seen something. Hello, 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 I've seen something. I'm measuring it on the computer screen. You can see it now. Hello, are you paying attention? Sometimes I think I need to do that in the videos as well, right? And then after the sample goes through the combustion tube and it generates the CO2 that it needs to generate, there's no more sample there, right? That sample is now over. So there's going to be less amount of CO2 that gets formed, and you'll see it come back down to what we call baseline. That is kind of what you would see on your computer screen when you begin to run samples. All right, well, the issue here is that this, some people will call a peak. That's okay for us to call. This is a peak. And I see that on my computer screen, and that is a area that's going to be very important because that's going to relate to concentrations and amounts of CO2 that were there. A couple of things that can happen though here. One of the things that you might see is a flat line and then a peak that comes up and then maybe comes back down, and then another jagged little peak that forms after that, and it comes back. All right, this is something that we don't necessarily want to see. This is a clue that something is happening inside of your instrument that needs a little bit of attention. And I'll talk about that in just, a minute or two. Another thing that you might see on your computer screen is maybe a flat line that happens here in the beginning, and then a very slow incoming peak, and then something that kind of comes back down and rushes back down to the base. This is very wide. It is very, it's not steep at all, right? This is going to take its time to actually form on the computer screen, and we have an issue. Another thing that could happen is that here you're going to see a peak that immediately forms, but yet when that happens, it takes its time to come back down to the baseline again. And we see an exaggeration over on the other side as well, right? Just like here in the very front one. And maybe let me make this more exaggerated just so you can see the difference. There we go. So there's going to be a few issues here that we want to look out for, right? The detector doesn't know this. The detector's only seeing these things, and it's just reporting you these numbers, and that's all that it's doing. It doesn't know that there's something wrong. I mean, this is part of the user. This is part of the analyst. This is kind of part of why you're taking this class. So you will understand what these diagrams are kind of telling you. All right, so first and foremost, I want to talk about the last one that I did first, right? With this last one, this is automatically seeing some CO2, but it's taking for hell and ever for it to come off. All right. So this is a very long analysis time. All right. It is taking very long for that CO2 to leave, which means that that CO2 is not getting pumped out of the machine at the proper flow because it's lingering. It's staying there. It's drip, 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 drip out. So this is really a problem most of the time with your air supply. Okay? If you have your air tank on and you're running samples and your air tank is at the proper pressure, the flow that goes into the machine, then these peaks need to be kind of straight up and straight down. And if you see this fat end to the right-hand side, that is a sign that it's taking forever for it to come off. Well, this is a very good indication that your airflow, something with your airflow is wrong. Your airflow could be blocked or your airflow could be low. So check the level of your tank. Make sure that your air tank is kind of filled up, right? And then you also want to check the tubing. So if there's a crimp in the tubing, whether it's on the outside or inside of the instrument, then that tubing could cause this kind of scenario to happen. So you just want to go through, check everything, check your tank, make sure it all looks good, but that's a common problem if that's what you see. Here on the left-hand side, this means that CO2 is getting produced and CO2 is barely coming out, little bit by little bit by little bit by little bit by little bit, and then all of it kind of comes off at once, right? But it's taking forever for it to come off for the detector to see it. This is a very good indication that there's something wrong with your combustion tube, okay? This combustion tube, if it begins to collapse, those beads, remember I said they're not going to stay spheres forever. They will start to turn powder. Well, as it becomes destroyed, it's going to be a little bit harder for your sample and stuff to travel through that combustion tube. So it takes a little bit longer for it to go through the tube and out the other end. Now, is this a sign of airflow problems too? Possibly, right? Yeah, sure. Airflow has something to do with your sample coming out. But on the front end, if we see it on the front end, this is more of a problem with maybe something that's happening on the inside of your combustion tube. So here, your pathways have been collapsed. The particles, they need to be regenerated. There could be some crud that's left behind that's preventing from the sample from flowing through really well. But this is normally a combustion tube problem. Then finally, the one up above. This is what we would call a split. This is definitely a sign of combustion problems. All right. So this is a very good sign that there's either something wrong with your tube or there's something wrong with your beads, and your beads are going to be the number one culprit. The tube, unless it's cracked, you probably aren't going to see a problem out of, or unless it's really old and filthy and disgusting. This is a very common problem of the beads that are collapsing on itself, and it is a very good sign. This is not an airflow problem here. All right, this is a very good sign that it is truly, truly bead-based and combustion-based. Okay, so why is this happening? Well, in your combustion tube, you're going to have all of these beads, right? And all of these beads are going to be loaded up in that tube, and you're going to have sample that's going to start flowing through. So here's your sample, and your sample will start to go through, and it will circle around all of these beads, and it will combust, and CO2 is made, and out the other end it goes. But notice what I did. It's like the game of Plinko on The Price is Right, if you've ever watched it. So there's multiple pathways that your sample can take as it travels through these beads. There are multiple options. Which way does it go around the bead? Does it go left-handed? Does it go right-handed? And then with the next bead, does it go left-handed? Does it go right-handed? So there's tons of different avenues and roads for it to take to travel through this combustion tube. All right, well, let's say that over a course of time, I've not paid attention to my beads, and my beads have now collapsed in a certain area. All right, so what happens is that my next sample will come in, and my next sample will start to split off, and it will go through all these pathways, and this one will keep on a trucking, and that one's going to get blocked. All right, and when that one gets blocked, it's going to take some time in order for it to figure out what to do. And eventually it will make it around that roadblock, but that will separate it from the pack. And it's not all going through at one time. So what's happening here is that sample's coming through, and a lot of that sample is coming through and it's going down, 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 but then there is a part of the sample that got held behind with the roadblock, and that detector sees that part which is lagging behind. And then it finally goes back down to the baseline. That is what we call a split peak. That split peak is typically due to the roadblock that is happening because my combustion beads have now decomposed and they need to be changed, right? Cleaning and regeneration is not going to solve this problem. Those beads have to be dumped. New beads have to go in. That way my sample can go front end to back end in one clump. That is what I want to see. Now, the splitting can also happen on the front side as well, which means that I could have a shorter peak here, which means less amount got through first and more of my sample got held behind, and then a taller peak that happens second. So it doesn't quite go back down to the baseline. So the larger chunk got held behind, and this is an indication that the blockage is extremely bad. It is a very large area that has been blocked. So some of my sample has escaped it, and some of my samples came out first, but the majority of my sample was held behind because it was a larger roadblock that was there that it had to get around. So either side, you're going to see this kind of encounter. So just a little bit about what a graph is supposed to look like from my detector, and maybe a little bit of indication about some of the problems that's going on inside of your TOC analyzer when this begins to happen as well. All right. So what I want to see preferably is something that looks like this, or what we would call Gaussian, which is a perfectly symmetrical peak that is getting generated on my graph. That is a picture perfect report from a TOC analyzer, but quite honestly, it will never happen. So that's something that we strive for. It's something that we want, but there's so many kind of moving pieces and parts and variables at play here that if we just get something close to one peak that looks pretty good, not perfectly Gaussian, we're okay with it. We move on to the next sample. Not a big deal. All right. The other thing that I want to talk about with the detector is the peak, right? So the peak is formed and there's my baseline. So what happens here is that the software will come through and it will look at where the baseline would be, right? So there's where the baseline would be before that peak came off. And my software will look at the area that is underneath that curve. Okay, so this is the area under the curve. And this is how it begins to assign how much CO2 was present and how it begins to assign the concentration. So what happens here is that I'll inject a standard, let's say a 1 part per million, and I'll get a little boop. That's about it. And then I'll inject a 5 part per million, and I'll get something whoop, a little bit higher. And then I'll inject, who knows, 100 part per million, probably not, but we'll just do that. And then I'll get a huge peak that comes up and comes down, right? So what it decides to do is that it will look at the areas under these curves. So this is the area for the 100. This is the area for the 5. This is the little area for the 1. And then I inject my sample, all right? So what it does is that it takes my sample and it looks at the area under the curve and it says, all right, well, where would that fit? Okay, where would it fit in here? This area is greater than 1, maybe. It's greater than 5, and it's not quite as great as the 100. So maybe my sample goes right in here somewhere. This is how the instrument and the software begins to calculate the concentrations for you. All right. In order for it to do this, what it does is a calibration curve. And a calibration curve will make a graph. And here's your 1, and there's your 5, and maybe here's your 100, and a line will be formed. Concentration will always go on the X, and your area will always go on the Y. So it knew at 1 part per million, this is my area. At 5 part per million, that is my area. At 100 part per million, this is my area. And it calculates a regression line in the form of y equals mx plus b. It will do this on its own. You can do this by hand using Excel if that's what you want to do, but the software will do it on its own. So it takes the area from the sample, and here area is your y-axis, and it takes this area and it plugs it in for the y variable, and it solves for x. And x is going to be the concentration in part per million. So here we can eyeball the area. We can kind of tell you, well, it's between maybe 5 to 100, somewhere in there. That's where my area is going to be. And then this is a way that it can really fine tune and hone in on that specific number. So it lines them all up. It makes a calibration curve. It gives you a line, y equals mx plus b. You take the area from the sample, plug it in for y, and you solve for x. And that is the concentration of your sample in part per million, because part per million is the unit that we used on the graph. All right. Good news, machine does it for you. You don't really have to do this calculation or math on your own. But at the same time, I also think it's very important for you to understand how it's doing its job. Okay. This calibration curve and your data is only as good as your calibration curve. So if you are messing up making standards, you will have a messed up calibration curve, and you will have messed up concentrations on your samples when you begin to run them. It's as simple as that. All right? It's all based on you, buddy. Okay, so this is where this video is going to stop. And in the next set of videos, what you're going to see are things that I would call support pieces. So these are pieces of the machine that are there that do a job, and we're going to talk about what that job is, but they're not what I would say completely necessary. It makes the job easier, it makes you have better data, but the detector, the beads, that combustion tube, the valve, and the syringe, that is really the driving force of the TOC instrument. All of these other pieces and parts, as you're going to see, does something, and it makes the process easier. And if they go out, of course I want to fix them, but they're not as major, okay, as some of these other pieces are. All right, so that's what we'll do in the next set of videos. Come back, we'll have a chat.